Hey everyone, and welcome to This Explainer. Today, we're tackling a massive, absolutely essential topic in system design. Our ultimate goal here? Figuring out how to take incredibly complex database systems and make them simultaneously reliable and, well, blazingly fast. We want systems that don't just survive a random hardware failure, but actually thrive and scale globally as an application explodes from a few hundred users to literally millions.
Okay, let's dive into this. Picture this scenario. You've built an incredible application. Millions of people absolutely love it. But all your user data, your configs, your messages, they all live on one single database machine in one single server rack somewhere. So what happens if someone trips over the power cord or the hard drive just fries? The answer is simple and honestly terrifying. Your entire application dies with it. It takes your revenue and worse, your hard-earned user trust right down the drain. It's a catastrophic scenario, all because you have a single point of failure.
So here's our roadmap for today's explainer. 1. The single database risk. 2. Enter leader-follower replication. 3. The read scaling superpower. 4. Handling leader failures. 5. Example, global messaging app. And 6. The trade-offs of replication. We're going to journey from a super fragile system to a robust global architecture.
Let's kick things off with Section 1. The single database risk, and why keeping just one copy of your data is an absolute engineering nightmare.
Relying on a single node is a massive vulnerability. Hardware failures aren't a matter of if, they are absolutely a matter of when. A single point of failure means you're risking permanent data loss, extended downtime, and you are completely hard-capped by the processing power of that one specific machine. On the flip side, a replicated system distributes that exact same data across multiple machines. This gives you fault tolerance, so if a machine burns down, your app stays up. It gives you high availability, and as we'll see in a minute, incredible scalability.
So how do we actually transition to that resilient system? Section 2. Enter the hero of our architectural story, leader-follower replication. At its core, replication simply means keeping a copy of the exact same data on multiple machines that are connected over a network. Now, if your data never changed, this would be trivial, right? You just copy the files over once and call it a day. But the real engineering challenge in distributed systems isn't copying static data. It's managing continuous, unpredictable changes happening thousands of times a second across geographically distributed machines, all without losing a single byte.
And this brilliantly illustrates the most common way to solve this continuous change problem, the leader-follower setup. Notice the architecture and the direction of the data flow. One specific node is designated as the leader. Every time a user updates their profile picture or sends a message, what we call a write, that request must go to the leader first. The leader saves it locally and then sends that exact data change out to the other nodes, which we call followers. It's absolutely crucial to understand that followers never accept writes directly from users in this specific model. They strictly listen for the change log from the leader and apply it to their own local copies. So, while only the leader accepts new data, any of the followers can be used by clients to read that data.
This brings us to Section 3, and honestly, one of the absolute best reasons to use this architecture, the read scaling superpower.
If you have an application like a news site or a social network, you usually have way more people reading data than writing new data. By having multiple follower nodes, you unlock massive performance benefits. Need to handle a huge surge in web traffic? Just add more followers to increase your read capacity. This entirely removes the heavy query load from your vital leader node. Even better, you can place these follower servers geographically closer to your end users around the world. The closer the server is to the user physically, the lower the latency, which creates a vastly smoother, faster user experience.
Now, what's really interesting about this timeline is that we have to make a crucial choice between synchronous and asynchronous replication. In a synchronous setup, the leader blocks the user's request, waits for the follower to actively confirm it saved the data, and only then tells the user it was successful. This guarantees maximum data safety. But if that follower has a random network glitch, your whole system stalls waiting for it. With asynchronous replication, the leader just shoots the message off to the follower and immediately confirms success to the user without waiting for a response. It prioritizes blazing speed, but introduces the risk that a follower might be lagging slightly behind.
Which naturally leads us to Section 4, handling leader failures. We've established the leader is vital because it handles all the writes. So what on earth happens when the main node suddenly goes offline and we need to recover?
Let's see how this automatic failover process actually builds a resilient system. First, the system has to detect the failure. Since you can't always tell why a node vanished from the network, databases usually just use a timeout. If the leader goes quiet for, say, 30 seconds, it's considered dead. Second, the system must choose a new leader from the surviving followers. It usually does this by checking their replication logs to find the node with the most up-to-date data. Finally, the system has to reconfigure itself so that all new client writes are instantly routed to this newly crowned leader.
But failover is incredibly tricky. Actually, scratch that, it's straight up dangerous. I want to warn you about a severe risk called split brain. This is a terrifying state where a network glitch causes two different nodes to simultaneously believe they are the true leader. If both start accepting writes from clients independently, your data will quickly become hopelessly corrupted and conflict-ridden. Handling failover requires incredibly careful engineering to ensure there is strictly only one leader at a time.
Let's move to Section 5. Example, Global Messaging App. It really helps to anchor these abstract concepts in a relatable scenario. Imagine you're launching a massive global chat application. Let's trace the journey of a single text message through our leader-follower architecture. You type a message to a friend and hit send. That write request routes directly to your database's designated leader node, which securely records it. Instantly, the leader pushes a copy of that new message out to its follower nodes stationed in different data centers across the globe. When your friend opens their app, their read request doesn't have to cross the ocean to reach the leader. Instead, a geographically nearby follower server delivers the read incredibly quickly.
But remember asynchronous replication? Because data takes physical time to travel through fiber optic cables, we operate under what's called eventual consistency. This means if your friend opens their app the exact millisecond after you hit send, they might query a follower node that just hasn't received the update yet. They won't see your message right away, but if they wait just a moment, that lagging follower will process the changelog from the leader and catch up, eventually.
And that brings us to Section 6, the trade-offs of replication. In system design, there's no such thing as a free lunch. Every brilliant engineering solution introduces new complexities.
To summarize the core engineering trade-off, on one side, we gain incredible superpowers like high availability, true disaster recovery, and the ability to scale our read traffic to millions of users seamlessly. But by doing so, we invite the villains, asynchronous replication lag, temporary data inconsistencies across our nodes, and the sheer operational headache of managing failovers correctly without risking data loss or those nasty split-brain scenarios.
In fact, you've probably experienced the symptoms of replication lag yourself out in the wild. Have you ever written a comment on a popular website, hit submit, immediately refresh the page, and your comment completely disappeared? You probably panicked thinking it was deleted or moderated. But then you refresh 5 seconds later, and it was back. No way, right? Well, that wasn't a bug. That was replication lag in action. Your write went to the central leader, but your incredibly fast first refresh was served by a follower that simply hadn't caught up yet. Your second refresh hit a fully synced follower, and your comment magically reappeared.
So I'll leave you with this provocative question to ponder. Replication buys you incredible resilience and speed, but are you ready to pay the price of distributed complexity? The reality is, if you want to build systems that survive and scale globally, you absolutely have to. But understanding these fundamentals is the crucial first step to taming that complexity. Thanks for joining me on this explainer, and I'll catch you in the next one.